Hi everyone, and welcome back again to my channel. So in today we're going to look at this circuit that we started with last week. We're going to look at the complete design, adding the receiver section. Just as the refresher from last week, we had introduced this system of using resistors to create different functions on the transmitter side of the 433 megahertz transceiver circuit, transmitter and receiver. And so the resistor network goes into the Arduino, and then the Arduino has an output signal that goes into the transmitter, and then the transmitter. So I'm just going to add the transmitter in this circuit here. So basically from the Arduino here, we go to a transmitter. So that will be in, and then the out will be to the antenna. Then you have the positive and ground. So basically this has power supply VCC, it has data, antenna, and ground. Not much here, right? So when this signal is transmitted to the receiver circuit, we looked at the receiver as well. So the receiver is as simple as the transmitter is. You have the VCC as well, you have the antenna, you have the ground, and then you have the data out. This is the ground, not capacitor, but ground, and then you have the data out. As simple as it can be. Now this out goes into an Arduino circuit, and we looked at the Arduino last week simplistically, but we didn't look at the Arduino. Sorry, we didn't look at the Arduino last week. We only looked at the receiver section and used an LED to indicate the output. So in today's tutorial, we're going to focus on how the Arduino section functions, and in next weekend we're going to look at using this with ATtiny, because the whole idea is to reduce this and put it in a very tiny microcontroller. So let's go into the system right away and see what we've designed. Again, looking at the transmitter circuit here, we have the same circuit from last week, the same code from last week. You already know how to read the resistors. We have fixed the value of R1, which is 2000 ohms or 2 kilo ohms. So this is the same as 2 kilo ohms. Right, and we have to calculate R2, and we originally assigned it a value of 0. Now we can put this code on the chart, on the description if it's demanded or requested. But here we're calculating R2. We know R1, like I said, and we're getting the buffer from V in over V out minus 1. Then when we multiply that with R1, we get the value of R2. So then we wrote our code to say if R2 is within this range, then write a function. We showed this last week. Write a function that's a signal generator with a delay. So there's let's look at that code here. We have a timeout there. We say go to this function and include that whatever time we've called out here in the signal generator. Use that as the timeout period. In other words, the on and off period is equivalent to this timeout we have here. So we'll write high and lows to data out. Data out, we have declared it as pin number 4. We did this on purpose because we want to use it for the ATtiny. So we started writing the code for ATtiny. We're just going to flash it to ATtiny without really changing anything on the code. Versus using like pin 7 or 8, which we don't have on ATtiny. I'll give you an example here. So let me just go here and change this to the board. I'm going to change the board to ATtiny 85, and then I'm going to compile this code for ATtiny 85, and we'll see if this code can fit into an ATtiny 85. And so you'll begin to understand why we're writing the code the way we're writing it. So done compiling, we only use 53% of the program storage and 49% of the variable global variables. So we still have space. So we can flash this code as it is on an ATtiny with no problem at all. And we don't have to change anything in the code. The Arduino Uno has multiple pins, including A0, A1, all the way to A5, I believe. Yeah. And then you have digital input-output pins all the way to 13. So you now understand what we're doing. We're using PB4, which is pin number 3. Pin number 3, physical pin number 3. So that will be physical pin number 3 on the Arduino, on the ATtiny. Sorry. Let me show you what I mean by that. So the ATtiny, the pins are this way. So let's do this with red. Maybe black is better. So let's do it with black. So pin 1, 2, 3, 4, 5, 6, 7, 8. Now, if you don't know how to number ICs, you go to our other videos on basic electronics to see how you number ICs. So the pins will be 1, 2, 3, 4, 5, 6, 7, 8. But the pin functions, this is reset. Pin 1 is reset. Then you have pin 2. So let's just name the ones that are standard, ground, and VCC. So these ones. Then you have your PB0 here, PB1, PB2, PB3, PB4. And then this reset is also PB5. They have multiple functions like MISO and MOSI is also pin 7. So I think this is MOSI, master out slave in, and this will be MISO, master in slave out. Something like that. I hope they're not swapped, but I think that's the way it is. So PB0, 1, 2, 3, 4, 5, 3, 4, and then 5. A way to memorize them, if you will, is to look at this across. 1 plus 4 is 5. 2 plus 3 is also 5. And then this one remaining is 5. So just the way I try to memorize things. So you have 0, then it goes up. 1, 2. The one that is opposite 2 is 3. The one that is opposite 1 is 4, and so on and so forth. So these are the pins. So when we use this pin, or this ATtiny 85, I think it is the same with 25 as well. ATtiny 13, 25, 45, 85. I think the pins are the same or similar. For most practical purposes, they will be the same. Now, in the future, when we use this code for our ATtiny project, we don't have to change the pins or the codes. We'll just use the code as is, and everything should work seamlessly. So we know the value of R2. We calculate that from here. So when you push a button, the code is checking if the value is between this and that. The range is really wide. The range is a little bit wide. If it's within that, then write this delay. This delay is equivalent to 1 kilohertz. So let's show the math and how we're able to calculate that. So the delay or timeout is 1000 microseconds. This is equivalent to 1 over 1000 seconds, right? Because 1000 microseconds is the same as 1000 over 1 million. So this 3's and that 3, so 1 over 1000. And this is the time, right? So this is the duration, the time, the on time or the off time, since this is uniform, so it's a square wave. T on and T off, time on and time off are equal. So T on is equal to T off, right? So I can put 3. So T on is equivalent to T off. Equivalent to T off. All right. So that's what we're trying to demonstrate here, so that your frequency will be half T off. We know that frequency is 1 over period. 1 over period, right? So this already is, this is 1 divided by 0.001 as a frequency. And that will give you something like 1,000. 1,000, just 1,000, not kilohertz, but 1,000. However, this is assuming that we're using just 1/2 of this pulse, but we're using both of them to create the frequency. That means we're going to multiply this by 2. So that 2 divided by, we're going to multiply, sorry about that. So this is going to be 2 here. Yes. So 1 over, so instead of 1,000, here is going to be 500. 500 hertz. All right. So that's the frequency. Again, we're doing this because the period is the time from one ongoing to the next ongoing transition. So first ongoing to the next ongoing transition is the full period. So time on plus T off is the period. And then, so in other words, the period, full period is 2T on or 2T off. So call this period T on, call this T off, then the T is equals to T on plus T off. So that T is equal to 2T on or 2T off. So that's why we get this value here, which is 1 over T here, but this T is T on plus T off, 1 over T on. Okay, we don't have to repeat that again. We can be a little bit smarter. We'll just say 2T on. So that's how we get this value here. Then that gives us 500 hertz. All right, so you do that for the 1,000. You're gonna do the same for the 2,000 and 3,000 and 4,000 and 5,000 and so on and so forth. So if you want to do that for 5,000, you just change the value to 5, and then you do the same. All right. So in other words, instead of doing that over and over again, since we have everything went from 1,000 to, let's just look at the code one more time. So we have 1,000, then have 2,000, 3,000, 4,000, and 5,000. So what we're gonna do is just to multiply by 1 over that or divide by that. So what I mean by that is for 1000 we got 500. So for 5000 microseconds, we're just going to divide this value by 5. That gives us 100 hertz. You can follow the logic down the same way, because if you have 5000 here, then 1/5000, instead of here having, remember you're going to multiply it by 2, so 1/5000 is going to give you 0.002. So 0.002, and then you're multiplying that by so where is that? Where is the formula here? Okay, so this is what we're looking for. Sorry about that. So we have 5000 divided by 1 million. 3 goes against 3. That gives you 5/1000. Right. So then when you divide 5 by 1000, you're getting around 0.005. Not around, but exactly 0.005. Then this is just T on or T off. So you multiply by 2 to get T. So I'm just making it shorter. So I want to get T. So that gives me 0.01, right? Because 2 times 5 is 10, so you have this 0.01. And then you just convert this, the reciprocal of that. So your F is 1/T, which is 1/0.01, which is basically 100. So, but instead of going through this, you can see why I just jumped to writing this value here. Instead of going through that, you know that the first one, when we did 1000, we got 500. So when it is 5 times more, then you divide by 5000 by 5 times. So when it is 3 times more, you divide by 3. When it's 4 times more, you divide by 4, and so on and so forth. So when we got, for the first calculation, we got 500. So we got 500 for 1000. That's the basic for us, 500. Then when it is 2000, that is 2 times more. From 1000 we got 500. When it's 2 times more, it's going to be 500 divided by 2. When it's 3 times more, 3000, it's going to be 500 divided by 3. When it's 4 times more, it's going to be 500 divided by 4. When it is 5 times more, it's going to be 500 divided by 5. That's how we got 100, 125, 133, no, not 133, 160 something. Because 26.2667, yeah. And then when it is 2 times more, it's gonna be 250. And so on and so forth. Okay. So we know that the pulse width or the frequency of each of the time we are sending from the transmitter. So we'll send this from the transmitter side, and then we'll go to the receiver side. Let's go to the receiver side. On the receiver side, this is what we're actually doing today. On the receiver side, we're using this pulse in function of the Arduino. There are two ways of looking at these pulse in functions. There is the pulse in long and then pulse in. Pulse in long is when you're looking, when the pulse width is long. For pulse width, pulse in, not pulse width, sorry, pulse in long and pulse in. For pulse in, when the pulse is less than 3 seconds. Now you see why we're doing all those calculations. If the pulse is less than 3 seconds, then you can use pulse in. If it's longer than 3 seconds, you want to use pulse in long. For pulse in, you have to declare no interrupts while you measure. Then after you measure, then you can start the interrupts again. Otherwise, some functions might not work properly. For pulse in long, you want interrupts, right? So you don't declare. If this is pulse in long, you don't declare this. Then you have to do pulse in long here. Okay. And then since you didn't interrupt it, you don't have to declare this. So just pulse in will be this. So you can use this to read for pulse in long. But in our case, we're looking at just pulse in, which is less than 3 seconds. There's none of our codes is more than a second delay. What we have, let's go back there. And you can work this backwards too. You know all our frequencies. None of this is up to a second. Is more than a second, let's say. None of them. So if your pulse width is more than a second, so from on, off, if this width is greater than 3 seconds, then you want to use pulse in long. And when you're using pulse in long, you can allow interrupts. Okay, for pulse in long. But when you're using just pulse in, so first of all, you have to declare no interrupts. Then write your code or the function you want to declare here, and then you allow interrupts after. Okay. Yeah, I think I'm missing R's in my interrupts. All right. So that's what you do. So for pulse in long, allow interrupts. So in other words, don't declare the no interrupts. And then for pulse in, declare no interrupts before you start your measurement. This is the code to measure the pulse width. So here you're measuring pulse width. Then after you measure the pulse width, then let me just write this properly. Yeah. So after measuring your pulse width, then you declare the interrupts again. This is T, not B. Writing on my screen, and sometimes the screen is shaking, and I'm trying to write fast as well. So I declare the interrupts again, so your code doesn't malfunction later. So here what we're doing is we're waiting for the pulse to go positive first. When it goes positive, we start measuring. That's why we're saying high here. And then once it goes negative again, we'll stop the measurement and we'll declare whatever value. We call it the pulse. You can call it pulse width or whatever you want, but whatever the value is, you can now check if it's more than a certain value, then do certain things. The reason for this is just so it doesn't keep running. If the pulse is less than this, just ignores it. If I press it shortly, quickly, and it detects only a brief pulse that is less than 1000 microseconds, ignore it. Don't do anything. I don't want you to start printing things out and stuff like that. But if it's greater than this, so 1000 and any fraction above that, then it can start to generate these functions. I'll show you what I mean when we start the test again. All right, so let me just go back to that. So basically, the Arduino, you declare the input pin, and the Arduino is monitoring that input pin constantly. So the moment it transitions to high, it starts measuring. And it will start a millis or micro, start a time, an internal clock to measure from the moment it goes positive. So it will start time, start clock. And this clock is ticking until it starts going. Once it detects a negative going edge, then it will stop clock. Then it will do a math internally. It will say T, so this is T0, or let's just call it T1. So let's say T0 is when the Arduino started running. So this is T1 and then T2. So pulse then, as we wrote the code, is equal to T2 minus T1. So this is the value that it will spit out for you as your pulse. Now you can change the code to be false or low. So in that case, if it starts at T0 and it won't really start doing anything until it goes positive, and then it will still not do anything, it will wait for it to go negative, because it starts when whatever condition you have declared is true. So this will be T0, T1, T2, but this is the start of the measurement. And then when it starts going positive again, on the positive going, it will be T3. So it will start clock here, start. And then it will stop clock here. And in this case then, your pulse is T3 minus T1. Sorry, I'm sure you figured out I made a mistake. T3 minus T2. So this is the pulse that you're measuring. I'll explain what I mean here. So if I go back to the code and I change this from high to low, I'm giving the Arduino instruction to detect the low going edge and start the pulse measurement or the pulse width measurement. And when it changes from that low to high, I need you to stop measuring and tell me how long it took. That's the instruction I'm giving it. So I'm saying when it starts with low, it's already low. It doesn't know when it started, when it went low. It's somewhere beyond T0. I don't know when it went low. If it's always low, I don't know. But then once it transitions to high, I'm monitoring it to go low. When it goes low, next time I will start measuring. So when it's going low is my trigger, is my interrupt to say start measuring. When it starts going high again, then I will stop measuring and tell you how long it took from one low going edge to a high going edge. That's what you're asking for. If you go back here, this started at T0, but it doesn't start measuring because it doesn't know when it went low or when it went high before. It waits for me to go high and then it starts the clock. When I try to go low again, it stops the clock and gives me the pulse. The same will be true if this started with a high. If I started here with a high, this system doesn't know when I was high, when I went high first, so it doesn't know. It wait for me to go low and then wait for me to go high again. It is then at this point of going high that it starts counting. And then when I go low next time, it will stop. So this will be my start. This is my stop. In this case, the pause will be here. So this pulse in, again, depending on what you wrote in your code, we only start at the edge and stop at the edge. So if you told it high, it will start at a high going edge and stop at a low going edge. If you told it a low, it will start at a low going edge and stop at a high going edge. So in my code, if I said high, let's write it proper. Well, the implication is, when does it start? When does it stop? So we start at a high going edge, at high going. Okay, I'm just gonna write it high going and stop at the low going edge of the pulse. When I say low, it will start at a low going edge and stop at a high going edge. So that's the way it's going to function. Okay, so we'll go back to the code so you can understand this better, and you understand why when it was already high, when it starts, it doesn't really matter. It doesn't really count. If my code is high, I'm going to change this color. If my code is high and assume this point to be the starting point, and it was already this way, it doesn't really matter. Even though it's high, it waits for me to go low first, finish my low period, and transition high again. At this point of transitioning high will be the start. And then it will stop when I start going low again. Then it gives me this width. If it started, let's change this color to yellow. If it started with low, then the moment it starts going high, that's when it starts. It could even be right here. Doesn't matter, but once it starts going high, that's when it starts to measure. And then when it goes low again, it will stop. It must be on the high going to the low going. Likewise, if my code says low, then if this was already high, it doesn't matter. You wait for me to low going, then it will start. When I'm high going, it will stop. Likewise, if it was low already, it doesn't matter now. It has to wait for me to go high and then start going low again. Then it will start. Then when I go high, then it will stop. Okay. So that's what is here. So here we're saying high. The original code says high. But we have this period to wait. If I did nothing, after 5 seconds or 5 million microseconds, then it will do something else. I can write an instruction what you should do, when this timeout is exceeded. But again, because I am using pulse in, not pulse in long, I'm going to allow my interrupts. I'm going to say no interrupt first and then allow the interrupts after. So just before I start measuring, I don't need to be interrupted. And then while I'm measuring, I don't need to be interrupted. When I finish measuring, then you can interrupt me. All right. So it doesn't accept interrupts. All right. During that period of measuring. If it's less than 3 seconds, this is your ideal. All right. If it's more than 3 seconds, then you have to find it. You have to use pulse in long, like I said earlier on. And then again, if there's a jitter, ignore it. I don't need to print anything out. If it's more than that, then print out something. And then I said, if the pulse width is between this range, tell me I have pressed the first button, and then I actually wrote this code for the 80 tiny. So I'm going to display using the LEDs, just based on what I told you last week. Using the LEDs, I can indicate what button has been pressed. So it will go low, low, high. So if I go back to the one note here, so you remember your digital logic. So you have A, B, C. So A, B, C, and then you can have your F if you're doing AND logic and whatever, but I don't need that. Just giving you an example. So I said low, low, high. Then when I press 2, it's going to be low, high, low. 3 is going to be low, high, high. 4 is going to be high, low, low. And 5 is going to be high, low, high. So that will tell me 1, 2, 3, 4, 5. So bearing that in mind, you can see low, low, high, low, high, low, low, high, high, that's 3, high, low, low, that's 4, and high, low, high, that's 5. So when I press, when the pulse width is greater than this period, then I press button number 5, and you can control these LEDs in this way. Again, you can make it do anything. You can make it go high, low, fly high, fly low, go right, go left, turn around. You can use this to control a robot. You can use it to control anything, any function, light bulbs, whatever, LEDs, and so on and so forth. You can use it to control anything you want. All right. So let's demonstrate this, and we'll call it a day for today. Alright, so here's the circuit we've been talking about all this while, and on the screen you will see the serial monitor right there. So when I press the first button there, it tells me the pulse width, gives me the size of the pulse width, and then also tells me it was the button number 1 that I pressed. So it tells me button number 2 has been pressed, and gives me the pulse width as well. So I'm going to move this to the other side because the video is blocking it. Then I'm going to press the third button here. It tells me button number 3 has been pressed. And then let's just clear it so we can see everything clearly. And then number 4, button number 4 is pressed, and then number 5. One of my resistors is shaky, so I'm not getting it to 3, 4, 5. So 5 is not, okay, yeah, it's working now. So again, this is one of the problems we have with breadboarding. If the components are not, touching as it should, you don't get it to function. And then again, why I left this LED in as a debugging LED, because if the button is not functioning properly, like it just happened a while ago, you wouldn't see this LED blink. All right. And sometimes I can press 5 and it tells me 4 because I didn't hold it long enough to measure the pulse width. And if I left it quickly, so let's clear this and show you what I mean. I just press it just fast enough, and it's just above 1000 microseconds, so it can do something. Remember in the code we said if you're less than 1000, do nothing. So if it's less than 1000 microseconds, it wouldn't do anything. But here we're able to get it just above 1000. So let's look at it again. We said if it's less than 1000, do nothing. Here. So unless it's more than 1000, then do something. But here we were able to get it just above 1000, not long enough to tell us what button has been pressed. Now, let's do this one here. Just long enough. Just long enough again. But now the value falls within the value for the first button, but I didn't press the first button. So explore in your own tutorial, in your own videos, in your own projects, how to use the bounce switch for this function. Again, we're using only one input output pin from the Arduino. One input output pin, because our target is to put this code in an ATtiny. Right, so we want to save space and also save our Arduino Uno and Mega and the rest of them, and just put every code in an ATtiny. So if I'm really controlling a function, I need to hold the button down for a couple of microseconds to give me the reading, then press another one. If I'm controlling a game, for instance, or controlling a robot flying a plane, I have to actually hold it, so, for a little bit. Okay. Right. C5 is not working again. LED is not blinking. Resistor is not properly connecting, or the switch is not properly connecting. Okay. Yeah. So solder it if you want to use this for a project. Make sure it is soldered. If it's not soldered, you cannot guarantee the function. Right, if I have soldered this, and it worked one time, it should work always. But because I haven't soldered it, all the wires flying around, the resistors hanging around, you can have some problems. Alright, in the next weekend's episode, we're going to show how to put all this code in an ATtiny. We've shown that already, so you can go ahead and do yours, but we're going to demonstrate this in our next week's episode. We will put this code in an ATtiny and just clean it up a little bit more. Alright, I want to thank you for sticking around to the end, and I want you to like and share this video. If you have subscribed to this channel, thank you. If you have not, please go ahead and subscribe. We're putting more education on this one, and then just the core videos on the other channel. Maybe 10 minutes video, maybe less than 15 minutes video on the other channel from now going on. And here we'll be having longer videos. So if you want to learn some of the things that we do and why we do it, you have to come to this channel, Hacker World. And if you just want to see the quick videos, you can go to HackerNet and just watch the same videos, but just a short version of it. That one is always shot first before we do the longer videos. Alright, and now until we come your way again with more content, stay enthused. Thanks, my friend. Stay inspired and keep building, keep coding. This is where we are at today, so keep coding, keep learning, and keep going forward. I'll see you again next weekend.